Hello and welcome to the first Tech Challenge Mechanical Design Workshop to Successful Robot Design and Function. My name is Matt Rainey and I'm the head mentor of Valley X Robotics and Plus3 Robotics. A little history on our teams. We are the 2015 FTC World Champions. This is our 13th season in first. We've been to the World Championships 5 times. We are the Inspire Award winners 2 times in Arizona. And we're based out of Valley Christian Schools in Chandler, Arizona. An agenda for today, we're going to go through the design process, kit parts versus custom builds, CAD software, SRA, and DEMA. What is the design process? The design process is what you're trying to do to get to your final design. In this case, we're going to evaluate the game. We're going to research different ways and design different ways of how to build an element or a system. We're going to prototype and test that system or element. We're going to continue the cycle, evaluating, researching, designing, prototyping, and testing until we get to that final design. Engineering is iterative. We're then going to get into the basis for design. In FTC, we've got kit parts and we've got custom. With kit parts, a couple of them that we're going to go over today are Tetrix, Actobotics, GoBuilda, Rev Robotics, and AndyMark. And with custom, that's building from raw material or from scratch. With the kit parts, the first one we're going to go over is Tetrix. It's a first sponsored kit, discounts through the storefront. It's based on an 8mm hole pattern, or is also known as a 625 scale. This is more important as we go down the list. The downside to it is it's very limited on the amount of items within the kit, but they do sell one of the legal batteries for FTC. Actobotics, which is a very big favorite of ours on our team, is from Servo City. They offer a 25% discount for teams that sign up. They offer yearly grants. They're based on a 7.77 to 1.5 hole pattern, but have adapters back to that 8mm or that 625 scale. They also sell the modern robotics motors. One of the big items that we like on my team is the servo blocks. Servo blocks will save your servos from being damaged for the most part, depending on how you design your robot. But using a servo block, even if you aren't using Actobotics, will save your servos tremendous amount of pain during the season. Tremendous amounts of pain during the season. GoBuilda, which is also the same company as Actobotics, is their metric version. You can find it at gobuilda.com. They also offer a 25% discount to teams that sign up. There's yearly grants that they give out, and they're based on an 8mm grid pattern. If you notice, that 8mm grid pattern, or that 8mm, is quite popular in FTC. They also sell the modern robotics motors that are legal in FTC. We then get into Rev Robotics. Rev Robotics is a first sponsored kit with discounts through the storefront. You can find more parts at revrobotics.com. In 2020, they're offering $25,000 in scholarship grants that are available on their website. And they're based on an extrusion channel bracket system that also has an 8mm hole pattern to it as well, to allow you to cross-work different types of kits. All of these kits semi-work together based on the 8mm hole pattern. Takes a little bit of work, but you can definitely mix match a lot of these different kits. Mix and match. The difference between Rev Robotics and everybody else, they're based on a 5mm hex-based system, which means you have a minimal amount of set screws. And if you ask any veteran team out there, you will know that set screws are not your friend. They have motor and gearbox options available, and those motors also come with that 5mm output shaft on their motors. Anymark.com, which is also a First Kit of Parts sponsor for First. You have the prefab tile kit that you can buy from them. That comes in either a 6-wheel drivetrain, a Mecanum drivetrain, or a couple of different other options. You can see that right here up in the top. They have multiple wheel options. Our favorite are the Stealth wheels. And even as a coach, these are some of the cheapest option wheels on the market and are some of the best wheels on the market. You can also get sprockets and different motors from a 3.7-to-1, 20-to-1, 40-to-1, and 60-to-1. They're typically stronger than your Tetrix motors in general, and are also based on an 8mm hole pattern. As I said, there's multiple wheel options available. Let's take a look at the Stealth wheels here. You've got a gray, black, blue, green, and orange. If we look at the gray, those will last you more than one season. You could probably get through multiple seasons through that. The black will last you a season, and the blue will last you an event. I do not suggest driving the green or the orange wheels on your drivetrains. Valley X, when we drive with a 6-wheel drivetrain, we go with the black and the gray ones. If we know that there's a pushing match, we may switch to the blue ones. If you're going with a Mecanum drivetrain, at least with Anymark, I would suggest the HD wheels. They do offer a cheaper, much cheaper set of wheels, but to save yourself some heartache and pain, please don't go with these as they break quite easily, especially in matches that have defense. And with this year's game and in an open field, there's definitely going to be some pushing and shoving around the field. Gracious though, you know that. So I would suggest the HD wheels. Then we're going to get into the pros and cons of a kit of parts versus a custom build robot. What are some pros of a kit of parts? It's quick and easy to prototype. It's easy for more inexperienced teams. And the information is widely available online. Some cons though, the cost is usually higher and you're limited depending on the kit that you choose. With a custom, the pros are it allows for a much cleaner look and usually costs less than a kit of parts robot. Some cons though is it may take longer to build and is harder for less experienced teams. It may need some more advanced tools. With Valley X Robotics, our veteran team always runs a custom robot near the end of the year, but we also use a kit of parts for our prototyping and for our rookie team. Both ways of building robots are perfectly great, perfectly fine. Some examples of kit of parts. Some of these kit of parts robots, as you can see, also have a few custom pieces on them. The wheels you see here that you might be questioning yourself on are Anymark wheels. This is a Tetrix robot, also a Tetrix robot. This one has a few custom pieces in it. It is a scissor lift. Here are some custom robots. These are of our teams of past designs. The robot you see here in the middle is actually the one that won the World Championships in 2015. Now we get into CAD. What is CAD? CAD is computer-aided design. There's two companies out there that sponsor First teams, which are SolidWorks and PTC. And you may be asking yourself, why would I want to do CAD or computer-aided design? Wouldn't you like to build your robot test it, design it, and see if there's any issues before you ever build it, before you ever spend a dime? I know the coach's eyes just lit up. Yes, you can completely build your robot, design it, make sure that there's no issues, and do multiple different things within the CAD software to see how your robot would look, perform, and act on a playing field before you ever have to spend one penny. Look into the computer-aided design. From these two companies, you can get sponsorships and don't even have to pay for the software. Now we're going to get into SRA. For those veteran teams, you may know what I'm already talking about. It's the speed, the reliability, and the accuracy of your robot. For a robot to be high performing on a high performance field, you must have all three of these things. Without one, you're not going to perform as well as one that does have all of them. You need to have that speed, that reliability of your robot, and that accuracy of that robot and what it's doing. We're going to put that up top, and we're going to look at design smart and smart design. And what do I mean by that? With a design smart, you're going to design what is best for the manipulation of these rings and wobble goals this year. You're going to design your robot to have easy access to make sure that you can fix whatever breaks. And maybe you're going to even add some adding and removing capabilities of either elements or parts of your robot, as well as the rings and wobble goals. Remember that you have to be able to get those out of your robot at the end of a match easily, or else you face penalties. With smart design, we're going to put in sensors and the use of them within the robot. Under SRA is what we call at ValleyX DEMA. DEMA is your drivetrain, your electrical system, the manipulation, and the automation of your robot. The drivetrain. One, it's the most crucial part of your robot. A weak robot will destroy a robot. A weak drivetrain will destroy a robot. Different types are wheeled drivetrains, tanked tread drive, Mecanum, and Omni, and those are the four we're going to go over today. Why, you may ask, is this the most crucial part of your robot and maybe not my electrical system? Let's say you have the greatest electrical system in the world, but your robot's sitting on the floor with a wheel falling off. What's that electrical system doing for you? You need to make sure that your drivetrain does not fall apart, and if it does, that it can keep moving and working on the field. So that great electrical system you have works perfectly. Make sure you can move around the field. Even if your manipulation fails, you can still play defense on the field and be a team that teams are looking at using in the elimination matches. With a wheeled drivetrain, we're going to go with 6 or more wheels. Some pros: any commercial wheel, for the most part, is allowed. Look at the rules to make sure that you're getting a wheel that is allowed. There's one at least that I know of. I don't know of the actual number, but it's within the rules that you can use are allowed. Some other pros: it's easy to push others around in defense, and it is normally tank driven. For your programmers, this is the easiest programming to do. Some cons though: it's harder to line up and there's harder movement around the field. With a tank tread drive, some of the pros: the appearance is very inviting for most students. Traction against the pads is tremendous. It's harder to be pushed around when you're playing some defense. And again, that easy programming is it's normally tank driven. Some cons though: it's harder to line up. If you're using Tetrix treads, it slides on wood, paint, and plastic. And if you're using those Tetrix treads, if you don't align them correctly, they will pop. And what happens if you lose one side of your drivetrain? You're not driving in a circle or not at all. Mecanum drive, some pros: You can move anywhere. It's easy to line up. It's easy to avoid those pushing matches. And if you go with the more expensive wheels, with a Mecanum drive, you might have some of that traction that we're talking about already. The cons, though, the better wheels are more expensive. If you don't have those wheels, as I said, it's easy to avoid pushing matches as a pro. So if you can, don't get into a pushing match, because one of the cons is easily being pushed around. It does require a motor per wheel plus an encoder per motor. And for your programmers, it's pretty extensive on the programming. So that means, mechanical team, that your programmers need to have the robot from time to time. Even if you aren't going with a Mecanum or an Omni-wheel drive, make sure that you give your robot to the programming team so that they can program your robot. You can build the best drivetrain in the world, but if your robot can't be programmed correctly before an event, what's it going to do? Some pros for an Omni-wheel drivetrain: it's easy to move around, it's easy to line up, and any commercially bought Omni-wheel out there is allowed. Some cons, though: it is the easiest robot to be pushed around. There's absolutely no traction. It doesn't matter what commercially bought item or commercially bought Omni-wheel you buy. It slides easily on wood, paint, and plastic, and there's that extensive programming to make sure that it works correctly. Some power transmission for your robot, and that what I mean by that is, how are you getting the power of the motors to your wheels? There's different types of ways. There's direct drive, belt and pulley, chain and sprocket, and gear drive. Gear drive. I'm going to let you look at these for a second. Some tips: if you're going with a wheeled drivetrain, do 6 or more wheels and stay away from those 4-wheeled drivetrains unless you're going with Omni, Mecanum, or Swerve. The reason for that is, if you have a 4-wheel drivetrain, you have one wheel fall off, you're now driving in a circle or not at all. If you have a 6-wheel drivetrain and that wheel falls off, you still have 2 wheels on one side, so you can still drive around and play some defense. Some other tips: direct drive will significantly lower the lifespan of a motor. It is more likely to break a motor. When you're building that drivetrain, try to stick with any mark Never Rest motors, Rev HD, or the Modern Robotics Go Build a Motors for your drivetrain. They're better performing than the Tetrix and the Rev Core motors. For higher speeds, use orbital motors, not spurs. And we'll get into that in a minute, what I mean by that. And for a normal speed, for what most robots use a 40-to-1 motor. If you'd like to take some more, if you'd like to have some more resources for drivetrains, you can pause the video here and you can copy down these addresses. Now we're going to get into the electrical system of your robot. This is the second most crucial part of your robot. You've now built a great drivetrain, so let's make sure that your electrical system is going to work how it should be, how it should. For the 2020-2021 season, in Game Manual 1, Section 7, it allows for Rev Robotics. This allows for either a Rev Control Hub, a Rev Control Hub plus Expansion Hub, an Expansion Hub up to 2 with a phone on the robot, and it also allows for those Spark Minis, the servo power modules, and the Blinkins that we'll get into later with the automation. If you are going to use a phone on the robot with an expansion hub and not a control hub, please make sure that you support those USBs so you don't have disconnections on the field and interruptions to your gameplay. Motors allowed for this year: with Tetrix, you have 3 spur gearboxes, which are 60-to-1, 40-to-1, and 20-to-1. This comes with a 6mm D output shaft. And what do I mean by spur motors? This is what you would classify as a spur gearbox compared to an orbital gearbox. One of the major differences, as you can visibly see, is the spur gearbox. The shaft is on the side, and the orbital gearbox, the shaft is in the middle. The reason for this is on an orbital gearbox, it's basically a ring of gears that is controlling the gearbox that slows down the speed of the motor. Whereas the gears inside of a spur gearbox are offset. When you need a stronger or faster drivetrain, the orbital gearbox is the way to go. With AndyMark, there are 2 spur gearbox options with a 60-to-1 and a 40-to-1, and 2 orbital gearbox options, 20-to-1 and 3.7-to-1. They also offer a no gearbox option. They also offer the Never Rest Sport gearboxes that they have, which have different gear ratios that you can choose from. And all of the shafts of these spur and orbital gearboxes have a 6mm D output shaft. With Go Build a Motors, or Modern Robotics, they offer 10 orbital gearbox options ranging from 30 to 1620 RPM, and they also come with a 6mm D output shaft. Now we'll get into Rev Robotics. With Rev Robotics, they have 1 spur gearbox option at 40-to-1. They have 1 orbital gearbox option, 20-to-1. They also offer a 90-degree core female output, which is 70-to-1. And what I mean by female output, it does not have a shaft coming out of the motor. You actually insert your own hex shaft into the motor to allow for the motor to drive that axle. They also offer a no gearbox option. They also have their own line of gearboxes called the ultraplanetary gearboxes. Those allow you to choose what gears you want within the gearbox and assemble them together. The major difference between Rev Robotics compared to the rest of the motors here on this list is the Rev Robotics comes with a 5mm hex output shaft. From there, we're going to get into manipulators. The manipulators of your robot are the 3rd most crucial part of your robot. How are you going to handle the game elements? We've built a great drivetrain and we've built a great electrical system. Now let's build a great manipulator system. Some types we're going to go over. We're going to go over conveyors, telescoping lifts, articulating arms, and shooters. With conveyors, we're going to go over 3 different ones here. We've got rollers, which use individual rollers, but this adds the weight and complexity to it. The balls or the objects will usually go in a rotating pattern. We've got double belted, which use a pair of belts. It increases the speed, but it also increases the complexity of the design. And it allows, again, for that quicker movement of elements. And then we get into the single belted, which usually uses a slippery material on the non-moving surface. Different places to find belts are McMaster, AndyMark, hardware stores, and there are other options out there as well. Extension lifts. There's multiple ways to control these lifts. You can do it with a winch and pulley and a rack and pinion. We're going to go over winch and pulley in just a moment. Some cons, though, is there's extra weight due to the overlapping of each slide. It can be difficult to manufacture depending on how you're building your robot. And there's friction that can be caused with slide binding if you don't get the slides correct. Now with a winch and pulley, there's 2 different ways that you can wire your lift. You can wire it as a continuous or a cascade. The continuous, as you can see here, Let's follow the red cable from the barrel. It's going up and over the tower and is completely winding through each and every slide up until the end effector, or the object, or the piece that is holding your object. We then use a yellow cable to then pull down the whole system, so we do not rely on the gravity and the weight of our system to bring it down. Cascade. The difference here is if we follow the red cable, it's going up and over tower 1 and is connecting to slide 1. We then have our yellow cable that's pulling down slide 1. The rest of the red cables, if we follow here, we're attached to the top of the tower, up and over slide 1, connected to slide 2. And we go over here, we're connected to slide 1, up and over slide 2, and connected technically to slide 3 because this is moving up the lift as well. Now we'll get into scissor lifts. The upside to scissor lifts is it allows for that maximum height with minimal amount of space. It's typically a strong lift. The cons, though, is it's very unstable at the top normally, and it's very complex to design. If you have not built a scissor lift yet, please do not do this during your season, and you'll thank me later for saying this. It takes a lot of work to get scissor lifts correct. Some lift tips. Where you can, use thinner walled material where it won't deform. Cheaper alternatives to lifts. You can use drawer slides picked up from Lowe's or Home Depot. You can manufacture your own parts. Keep in mind the feedback of your lifts. Use those potentiometers, those encoders and limit switches. Create an automatic take-back action based on error. What do I mean by that? Let's say your drivers drive the lift too far. The robot will then know that and pull the lift back into place before the lift completely breaks, if that's the case. Design in sensors from the start of your design. Keep in mind the speed versus volume of your lift. Optimize it for your strategy. And where applicable, design for a cascade type lift. This is the quickest type lift as all of the slides. I'll go back to the slide for you. As all of the slides here on a cascade lift move all at once. So as this pulls it up, this one and this one are moving at the same time. Whereas with a continuous lift, one moves at a time. And also think outside of the box. Now we're going to get into single jointed arms, multi-jointed arms, and 4-bar lifts. Let's do this as a example. Take your arm and put it out. Now keeping your elbow and your hand straight, not moving at all, move your shoulder up and down. This is a single jointed arm. It has one shoulder joint, typically the end effector, or in this case, your arm or your hand. It is the easiest type to build, and it follows the KISS methodology. Now let's move on to multi-jointed arms. Take your arm and start adding in the bending of your elbow and your hand. You've now added a degree of freedom, but that also added the complexity. Every joint needs to be engineered. While it's easy for you to be moving your arm up and down and your elbow in and out, you have to think about how the operator is going to control the device on the robot. Make sure you design and put in those sensors to allow your drivers to focus on what is most important in the game. We then get into 4-bar lifts. Linkages can help control arms. There's advantages to specified motion. With a 4-bar lift, the end effector in this case always stays parallel. and you can customize it for any application depending on where you drill your holes. And what do I mean by a 4-bar lift? If we look here in this picture, we have the tower, which is underneath this shielding here. We then have a second and third bar. And then if you look right here, there's the 4th bar going up. These two arms stay parallel, and it allows this to stay parallel. So if this goes down, this end effector will still stay at that angle. If it goes up, it'll still stay at that angle. Some arm tips. Where you can, use thinner walled material where it won't deform. I wish I had a picture, but if you look here in this, these arms used to be blue. We had to change it out for thicker material because after our first event where this robot was hanging, it deformed the arm. Every pivot point needs to be thought out and engineered. Every rotation point has different forces. Linkages can help control long arms and maybe counterbalancing those arms to reduce the work on the motors to help save the motor's lifespan. Keep in mind the operator interface. How are your drivers going to drive the robot? The KISS methodology, especially with arms, isn't bad. And keep in mind the feedback control is huge. Potentiometers, encoders, and limit switches help. That automatic take-back action based on error, and designing those sensors from the start. Think outside the box. Last but not least, we're going to get into shooters. I know everyone just went, ooh. With shooters, we're going to go over 3 major players out there. We have the flywheel, the double wheel, and the catapult. With a flywheel, it's typically one wheel fit within a hood. It launches items in an arc or it creates spin. The hood is typically fixed. The downside though is it's very complex to build. With a double-wheeled shooter, the wheels are in 2 different locations. It's fixed on each side of the shooter. It normally launches the item with a forward momentum, not as much spin. It's best run with one motor or one set of motors to control both wheels. Having a motor per set of wheels that are not connected together can create a little bit of shock, which will wear out the motors quickly. On a catapult, it typically launches one item at a time. Designs are normally slower than a wheeled shooter, but what the upside of a catapult is it's normally the same shot every single time, as it does not rely on the speed of the wheel. Some shooter tips, and this goes for everything really, on your drivetrain, your electrical system, and the rest of your manipulation. Look at past designs. Look at both FRC and FTC. I'll give you guys a hint. With this year's game of throwing rings, look at Ultimate Ascent from FRC. Materials with shooters, build it strong. A lot of forces are happening. There is no weight limit this year, so build it strong. Feedback is huge. Potentiometers, encoders, and limit switches. That automatic take-back action based on error. Designing your sensors from the start. Keep in mind speed versus volume and optimize it with your strategy. Wheeled shooters may require some wind-up time. Again, think outside the box. Last but not least, we're going to get into automation. And automation is both for autonomous and teleop. Let the drivers focus on what is most important in the game. This means both, again, for autonomous and teleop. Now you notice I didn't put this as the 4th most crucial part of your robot. This is crucial for your robot to compete and work high in the field. That feedback coming back from these sensors helps those drivers focus. The feedback from potentiometers, encoders, and limit switches can help speed up the robot, feeding into SRA. That automatic take back action error that feeds into the accuracy of your robot. It also feeds into the reliability of your robot. Design in the sensors from the start. Doing this will allow you to have the speed, the reliability, and the accuracy that your robot requires to compete on a high level field. If you guys have any questions, please visit the AZ FTC blog for our Zoom live call to ask me any questions you may have, or you would like to see any parts up close and, I guess not personal, but in front of the camera. I'd be more than happy to show you guys anything and everything that we have, and I'll see you guys then. Goodbye.